Hello, Dr. Chang and classmates. I'm Wayne Havey, and I'm going to be presenting a critique on a paper called Secure Opportunistic Multipath Key Exchange. So thanks for joining, and let's get started. So first I'll introduce the paper's authors and some of the goals that they were trying to achieve. So the authors are listed here on the left. I won't try to pronounce their names. They're mostly from universities in Scandinavia and Romania. So the goals that they were looking to accomplish via this opportunistic key exchange, which they shorthand to SMKEX, is they were looking to have a key exchange protocol that was opportunistic, that didn't have to rely on trusted third parties such as certificate authorities or pre-shared secrets. So we'll get into why they were not wanting to trust in third parties like CA authorities in the next slide. Additionally, they wanted to make their protocol simple and extensible in the sense that it can be easily integrated through existing protocols like TLS. Additionally, they wanted to have protection against certain types of attacks, so they have a threat model that we'll go over, and so they want to protect against active attackers, which they say most most opportunistic protocols cannot, and specifically unsynchronized active attackers, and we'll talk about what that means in a minute. So they wanted to implement their protocol over Multipath TCP or MPTCP, which is a fairly new implementation of the TCP protocol that makes use of multiple paths through a network in order to send traffic. So they wanted to be able to implement that through small kernel implementation changes as well as user libraries. So finally, they wanted to have a little modification to existing applications, hence why they wanted to have user space libraries and kernel implementations, so that existing applications that perform network communications don't have to make massive changes in order to implement their new protocol. So some more objectives and their motivation behind this, talking more about the certificate authorities. They believe that the process of using certificate authorities is tedious and recently has been under lots of attacks. So certificate authorities are an obvious candidate for malicious actors to attack. So they are often tricked into issuing certs to malicious parties, which has been fairly easy to do. If the servers themselves are hacked, taken control of completely, then obviously they're completely subverted in what they're meant to do. Revoking certs that have been deemed issued faultily has been problematic, according to the authors, difficult to revoke. And they often even intentionally will share secrets with what users may deem untrusted. So the authors talk about some existing opportunistic key exchange approaches, and they say that their approach is better or unique, and that most of the other approaches are resistant against passive attacks only, whereas theirs is resistant against active attacks. So passive and active, as we've learned in class, the difference there is passive is the attackers are only trying to view the data. They're not necessarily tampering with it, whereas active attackers will actively try and tamper with it. The authors also talk about these ideas called synchronicity. So if attackers are synchronized, then they can exchange messages between each other mid-session. So whatever type of protocol it is in the session that is established for that communication, they can pass messages between each other if they are synchronized. And if they cannot do that, they can only exchange messages before or after, then they are called unsynchronized. So their approach is to defend against unsynchronized active attackers. Additionally, some more motivation in the extensibility area is taking advantage of path diversity within network between autonomous systems or between nodes across the internet. There are multiple paths for messages to traverse in order to get from one point to another. So taking advantage of the diversity in paths is one way they want to make their protocol extensible by choosing different paths and using multiple of them, such as the Multipath TCP protocol. And as I mentioned previously, they want to integrate with other techniques such as TLS, so that's how they want to be extensible. So going into the protocol specifics, some background on that, and some more specific explanation on the actual SMKEX protocol. At its core, it's an extension to the Diffie-Hellman key exchange. So Diffie-Hellman does its exchange over one channel. So they want to extend that to make use of it over multiple channels, so multiple paths between a network past the different phases of that protocol via multiple channels. They want those channels to be public to make it simpler. They want to take advantage of the fact that the internet is widely moving to using multipath, such as multipath TCP. So there's wide availability of that, and they claim that that is getting more prominent, so they want to make use of that new feature in this protocol. Additionally, if there isn't enough path diversity between two nodes in a network or between autonomous systems, so if you're trying to establish communications to a node that is so close that there's only one or two paths, or something where it's difficult to have a lot of diversity, then they can extend their approach to create encrypted tunnels to basically create new paths within a short path to make sure that there is path diversity there. Additionally, their approach tries to accomplish forward and backward secrecy, which is a common objective for key exchange protocols. So forward secrecy is if an adversary is able to obtain all of the relevant key material for a specific session, they are not able to decrypt communications established in previous sessions. So the key material is not correlatable between sessions previous. And then backward secrecy is essentially the opposite. So given all key material for a specific session, they will not be able to decrypt sessions and communications established in the future from when they were given that key material. So establishing both those types of secrecies is important for this protocol. And then finally, the sort of main idea of the protocol can be described in this final purple box here. So they make use of multiple paths, at least two. So on one path, they'll exchange the key information. So in the Diffie-Hellman key exchange, they'll do the G to the Y. So the pre-established number raised to a power is the power is the secret key. So the Y is the secret key. They'll exchange their G to the Y from sender to receiver, and then on a separate path they'll generate a nonce or an n-once, which is basically just a random number generated specific to the session, and pass that on the separate channel, and then the receiver will pass back their private key number that's been generated, G to the X, for example, as well as a hash of the entirety of the elements within the exchange protocol on a separate path. So when the sender receives that hash, they are able to then determine the shared secret and compare a hash based off all the factors that they have now collected with the hash that was sent. And the idea is that because both paths can't be monitored actively as long as the attackers are unsynchronized, they can either see that they didn't receive the right key through the hash, or the protocol will just be terminated upon seeing that. So to explain this further, the authors had a nice diagram showing how the protocol works. So you can see on the left is the client side trying to establish a session with the server side, which is B, client is A. So the two channels A1 and A2. So as I mentioned, they'll send their key that has been generated using their private key of X, G to the X, to the server on one channel, so using one path between the nodes in the network, and then on a separate path they'll send their nonce that is specific to them for that session, so that will go across a separate channel. And then the server, or the recipient, the node that they're trying to establish communications, will send their G to the Y, as well as a hash of their nonce, the client nonce, and what they received as the client public key, and send that on a separate channel. So attackers can monitor one or both of these channels, but as long as both attackers aren't active and synchronized, then they will not be able to actually disrupt the integrity of the hash or the key, and so cannot sort of implement that man-in-the-middle attack where they collect both keys and then send messages to each as a man-in-the-middle, because they won't be able to corrupt the hash as well as create a new key. So this protocol is implemented simply using a user space library that's loaded before libc, so loaded before the standard implementation of network communications, so that applications that are trying to use MPTCP will use SMKEX before the standard methods of MPTCP. And then they did make a small kernel modification, and all their code is available on GitHub. And basically their kernel modification makes use of the MPTCP protocol that exists and uses an unused byte in the flags parameters that are passed to specify which subflow they're passing which piece of their protocol across. So the flag will specify in subflow 1 send the nonce, and subflow 2 send my public key, or something similar to that effect. So talking about the contributions and the results of the paper, first of all, in terms of the novelty of the paper, they did a good job of talking about related literature, brought in a lot of papers related to existing opportunistic approaches and how they do not protect against active attackers. They referenced a lot of literature for ways to validate basically the security of a key exchange protocol. So specifically, they referenced this paper a lot by Canetti and Krozik that basically defines a series of equations and variables to plug into that equation to model what the threat is or the advantage of the attacker is based on a protocol. So the variables in their equations that they propose are basically things like the session, how many sessions there are, and queries that attackers can make to something called a random oracle model, which basically allows is them simulating asking questions that they can get answers back about the session or about the keys or things like that. So they can ask questions based off the number of sessions and then basically derive this equation for the advantage of the attacker. So on the right upper hand corner there you get a couple of examples of the equations that are a little bit complicated to understand. They made use of this a lot and they had these equations in an appendix, but I think it would have required basically reading the entire Canetti and Krozik paper to fully understand what was going on with these equations, but this was their primary method of validating the security of their protocol. So in that top equation, it's basically saying the advantage of an attacker against the SMKEX protocol is basically 2 times the probability that the attacker can guess all of the elements that are used, so the hash, the nonces, and the keys, guessing those correctly, as opposed to just guessing a randomly derived key that wasn't the actual key, -1. So that's how they evaluate the security of their approach. So one important thing that the paper emphasized was attacking the attacker models. So we've already mentioned active versus passive and synchronized versus unsynchronized. So the authors, in order to describe how effective their approach was, broke down the types of attackers into these sort of 5 subcategories. So A stands for active, P stands for passive. If there's a bar in the middle rather than a dash, then that shows that those 2 attackers on separate paths, or that are monitoring separate paths in the network, are not synchronized, so they cannot pass messages mid-session or mid the session on the path that they're monitoring. Whereas a dash shows that they are synchronized, so an active attacker could pass messages mid-session to another attacker. So they highly emphasize that as synchronous 2 active attackers monitoring the 2 different paths would still be able to perform a man in the middle, but any of the other permutations would not be able to do so because the passive attacker can't modify the data, it can only see it, so even if the messages can be passed between the 2, the active attacker can't actually modify data on the second part, so they couldn't modify the hash or they couldn't modify the public key, only one or the other, so the integrity of one or the other is always preserved. Whereas if it was 2 synchronized active attackers, then mid-session they could modify the data being passed, so they could modify the hash as well as the public keys being passed and still perform that man-in-the-middle attack. So they talked about these different permutations of attack models, and so on the right-hand side, that sort of directed graph shows the different approaches, different attack approaches, and they say that if you can defend against one of the nodes and follow the directed line backwards, then you can also defend against that node. So for example, the synchronous attackers of an active and a passive points backwards to the passive, both synchronous and asynchronous. So if you can defend against active and passive synchronized, then you can defend against passive and passive both synchronized and unsynchronized. So that was sort of one of their methods for proving things. Based off that assumption, they showed that they could defend against active synchronized with passive and therefore could defend against both the passive attacker models. So they went into a lot of depth on basically path diversity and how that is effective and how they can actually make use of the path. They didn't really prove the security further than the formal analysis in the equations and further than just this sort of active-passive graph model. They didn't actually run tests where they actually had attacks actively running. So that's something that I think that they could do in the future, and that would be useful. So most of their results was based off measuring path diversity across autonomous systems across the globe. And then for a specific result that they were trying to show, they looked specifically into mobile clients and how two paths can be implemented from a mobile device by setting up one path going through the actual mobile data, the cell tower path, and one of the subflows for the other half of the protocol going through the actual wireless access point. So by default, you have built in two sort of paths that you can take to implement this result. So for some additional analysis and critique, overall I thought the paper was really well written. It was a little bit verbose, but they explained things very clearly. They had some really good appendices that went into depth on a lot of the concepts that were new, that were sort of corollary to their main ideas, and referenced a lot of papers so that you had some information to go off of so you could understand what they were saying. They did a really great job, and the beauty was in the simplicity of the technique. It's really simple to understand, but it's effective, taking advantage of what they say the internet is moving towards, which is this multipath TCP model. So I thought it was a really good idea and really well written in general. However, there were some things like the Krasinski or the Krasik method of formally analyzing the security of message exchange protocols. That was really sort of overly verbose and complex, and it wasn't easy to understand how it actually showed the security of the system. So it would have been, they should leave it in there, but it would be more effective if they did that, as well as in their experiment actually did some attacks on their setup where they actually set up VMs and implemented their protocol. So additionally, it seemed to me that they always assumed that the attackers were sort of separate attackers monitoring the paths. They didn't really do a good job, at least in my mind. Maybe I didn't pick up on it. If the two attackers, active and passive, were a single attacker or two separate entities. So it seems to me like a single attacker could monitor two paths, and then in that case, does it automatically default to the synchronized active attackers if it is the same attacker? So that's something that I thought the paper could have addressed a little bit better. And additionally, they did assume a lot of knowledge, even though they had those good appendices and some good related works. To really understand exactly what they were saying would require going a lot in depth on some of these other papers that they referenced. So I do believe that they validated their results in terms of making use of path diversity and validated the fact that the protocol can work. But they didn't validate, in my mind, the actual security in a real-world practical scenario. As I mentioned, they didn't actually run tests where they tried to attack their protocol in action. They only showed it theoretically via those equations. So they didn't have a ton of biases in that I could see. The only sort of assumption or bias that they made that made their approach seem more valid was the assumption that the internet in general is moving to a multipath TCP model. I would need more proof on that. But that did seem like the only bias, and it does make sense that would be the case. And their specific use case of the mobile data model was pretty obvious in the fact that you could use either the cellular data or your actual Wi-Fi access point. So it makes sense that it could be easy to set up. So yeah, that would be the only bias. And then in terms of practical relevance of this paper, it's extremely practical and extremely relevant in my mind, because the ongoing battle for secure communications is going to continue, and it's going to continue forever. And if it is true that we are moving to a multipath TCP model, having a protocol that takes advantage of that fact before it actually is fully adopted everywhere could be really important. So for some suggestions for this paper, I do generally agree with their statements that this protocol could work and can be robust, but I do suggest that they actually do some more tests, actually attempting some attacks in the real world setup that they have, in their lab setup at least. But other than that, the protocol is so simple that there doesn't really need to be much further verification. It just works. So for some future work that they mentioned was doing a formal analysis of implementing SMKEX with TOFU, or trust on first use. So through the SMKEX exchange, you could also pass in a long-term public key, such as what is used in like SSH sessions. So making use of that and doing a formal analysis of that technique needs to be done, and that's something that the authors mentioned, as well as setting up the TLS protocol and implementing that with SMKEX is some additional future work that they recommend be done. So as far as new research ideas, obviously, as I've mentioned, actually doing the attacks in an experiment, and then showing that this protocol works with more than just 2 paths. So they did briefly mention in an appendix that it doesn't have to only follow 2 paths, one for the public key and one for the nonce and then the hash. They could expand it to use multiple paths. I wasn't exactly sure, based off their brief explanation, on how they would split up the elements of the protocol across more than 2. So maybe the nonce on the return path could at least be a third subflow, but how would they actually make it use more than 2 paths seems like something that would be interesting that could go they could go more into depth on. And then an idea that I had would be to, if that is feasible to use more than 2 paths and have a stable way of doing that to exchange different elements of the protocol, could you dynamically change the number of paths that are being used in the exchange? So perhaps on a node midway between the node that's initiating the communication and the receiving node, could you split off the elements further to use 3 paths and then back down to 2, so that basically where the attackers have to be monitoring changes throughout the entire path distance, essentially. So I believe that those ideas could show some more proof beyond just the formal analysis, which would give this a little bit more efficacy. And then if they did implement the dynamically changing number of paths, that would improve security by removing some existing compromises. And by that I mean, if the attackers are monitoring specific paths and you dynamically change the number of paths and the way those paths are being followed, then the attackers would also have to do the same and dynamically move around and have to guess which paths are being used. So I believe that would improve the security even further. So that's the end of the presentation. Here are some references. Obviously, the paper that I presented, definitely recommend giving it a read. It was really interesting. And then the Kennedy and Krozik paper that goes into how to formally analyze the security of key exchange protocols, I thought would be something really interesting to learn about for other key exchange protocols that we learn about in the future. Thank you.